Hey, we're three guys. I'm Ryan.
I'm Kai.
I'm Brody.
And today we're going to talk about a phase diagram of our alloy. This is the phase diagram of our alloy, which is titanium copper. As you can see, it's pretty complex, but we're going to dive into it a little bit and show two examples of places where it is cooling. This is the first example. This is at the eutectic point, which is at 50% weight copper and 920 degrees Celsius. As you can see with this red line drawn right down the middle, it goes from the liquid state to the titanium 2 copper plus titanium copper state. On the left we have our first diagram, which is the liquid phase, which is 100% mass of liquid, and then we go over to 700 degrees Celsius, and we can see that it's 50% weight copper at titanium copper, and at titanium 2 copper we have 40% weight of copper. Now this is our second point where we are describing the cooling reactions. We chose 4% weight of copper, and it starts at the liquid phase at 680 degrees Celsius, and then it goes into the liquid plus the beta titanium phase at 600 degrees Celsius. Then it drops down to the beta titanium phase at 1100 degrees Celsius, and then it drops into the alpha and plus beta titanium phase at 800 degrees Celsius. And finally, it drops down to the alpha titanium 2 copper phase, and at 700 degrees Celsius. These are our wonderful drawings of each of these phases. So we start at 1680 degrees Celsius at the liquid phase. This is 4% weight copper, and all of it is liquid, so 100% mass. And then we go into the liquid and beta titanium, which is 6% weight copper for the liquid and 1% weight copper for the beta. And once we calculated the masses, we got 60% mass for liquid and 40% mass for beta. Next, we drop down to 1100 degrees Celsius, where we're just in the beta titanium phase. So this is just 4% weight copper, as it's just on the red line, and it's 100% mass. And then we drop down to the alpha titanium and beta titanium phase. Alpha has 2% weight of copper, and beta has 5% weight of copper. And the calculations have beta at 67% mass and 33% mass for alpha. And then finally, we drop down to 700 degrees Celsius, where we have alpha titanium and titanium 2 copper. Titanium 2 copper has a 40% weight of copper, and alpha has a 0.5% weight of copper. And the calculations got 91% mass for alpha and 9% mass for titanium 2 copper.
The next we're going to talk about the lever rule. The lever rule is used to determine the relative amounts of phases in a two-phase region of a phase diagram. So to the left here, you can see a phase diagram, and you can see the overall composition of liquid, composition of solid, and it's a rough diagram of how we would find those values. So to find the fraction of solid, you do C0, which is the overall composition, minus Cl, which is the composition of liquid, minus Cs, which is the composition of solid, minus Cl. For composition of liquid, or the liquid fraction, you would do Cs minus C0 over Cs minus Cl. And that's how you would find the lever rule.
So you may be wondering where we got our weights from earlier on. Well, they can be calculated using the lever rule. So, for example, we'll start with titanium copper and our titanium 2 copper. So for the weight of titanium copper, we take our concentration, C0, and we subtract it from the concentration of titanium 2 copper. We'll divide that by the concentration of titanium copper minus the concentration of titanium 2 copper. Doing that out, we get our concentration for titanium copper, or our weight for titanium copper, to be 62.5%. Our weight for titanium 2 copper can be calculated in a similar manner by taking the concentration of titanium copper, subtracting C0, dividing that out by concentration of titanium copper minus the concentration of titanium 2 copper. Doing this out, we find their total weight percent to be 37.5% for titanium 2 copper. We'll notice that the two weights add up to 100%. So now we can calculate the weights for our beta titanium. To calculate our weight for our beta titanium, we're going to use the following formula from lever rule. We'll take C naught, we'll subtract C of the liquid, and then divide that by the concentration of the solid minus the concentration of the liquid. Doing that out, we get 40% weight for beta titanium.
So Brody, what about the weight for the liquid?
That is a great question. Both of these weights percents should add up to 100. So therefore, the liquid would be 60%.
Nice.
Continuing on, for the weight of our other beta titanium, we have the initial concentration. We subtract out the concentration of the alpha titanium, divide that by the concentration of beta titanium minus the concentration of our alpha titanium. Doing that all out, we get 67% weight percent for our beta.
That's awesome, Brody. But what about the alpha?
Well, in a similar way, we can calculate the alpha by knowing that the weight percent needs to add up to 100. So therefore, our alpha should be 33%. Finally, we can do the weight concentration, or the weight percent for our alpha titanium. C naught minus the concentration of our titanium 2 copper, and we divide that out by the concentration of our alpha titanium minus the concentration of our titanium 2 copper. Doing all that out, we get 91% alpha. And again, to find the beta concentration, what we would have to do is we need to make sure that they add up to 100. So that would be 9%.